Hello and welcome to the ComPat webinar on multiscale modelling and simulation on HPC. We'll be taking questions at certain designated points as we go through the agenda today, so please save your questions for those Q&A segments. The ComPat project is a European Commission Horizon 2020 funded project that started in 2015 and is concluding this year in 2018. The full name of the project is Computing Patterns for High-Performance Multiscale Computing, and so this webinar on multiscale modelling and simulation on HPC deals very closely with the theme of that project. Even a cursory glance through the fields of scientific research reveals that the universe has important processes occurring on a vast range of length and time scales, from the quantum processes involved in chemical reactions such as photosynthesis, through the cells and organs making up life on Earth, all the way up to and beyond the evolution of galactic clusters. Scientists seek to understand what is happening on each of these scales. A powerful means of reaching this understanding is through computational modelling. Typically, and often for reasons of efficiency, we develop different computational models for each relevant scale of a problem. However, each scale does not exist in isolation. They are merely a conceptual tool, and to properly and fully model a complex process spanning multiple scales, all these solvers must pass information to each other, both up and down the scales of length and time. This is what we call multiscale modelling. In many cases, we find that processes on quite disparate length and time scales interact in strong and non-linear ways. The sheer complexity of such multiscale phenomena still limits our capability to perform high-fidelity simulations that accurately and reliably predict the behaviour of a given system in all situations. Capturing even a few of those coupled processes in a multiscale simulation quickly reaches the limits of contemporary high-performance computing at the petascale. Through access to the world's largest and most powerful supercomputers, we expect to be able to model ever larger and more complex systems. Advanced multiscale algorithms, in combination with emerging exascale resources, could help us transition to a predictive multiscale science. To make this possible, we shall need generic multiscale computing algorithms capable of producing high-fidelity scientific results and scalable to emerging exascale computing systems. We call this high-performance multiscale computing, or HPMC.
Good morning everyone. My name is Dirk Groen and I'm a lecturer in simulation and modelling at Brunel University London. I'm also one of the partners within the ComPat project. Within ComPat, I participate with the technical activities. I'm the lead developer of the FabSim toolkit, and I also contribute to the muscle framework. Today I'm going to talk about multiscale computing patterns. Multiscale computing patterns are a set of 3 patterns which you can apply to multiscale applications to combine different single-scale submodels in different ways. The idea of the patterns is that you can have a diverse set of applications mapped to one of these 3 patterns or a combination of them. In doing so, it allows you to map these applications very efficiently to large-scale resources. So, the essential point of multiscale computing patterns is that instead of manually transporting every application to exascale infrastructure, that you can focus on porting the patterns and then fit the applications within the patterns. The last thing is that the patterns have been assigned in such a way that they capture the vast majority of large-scale multiscale applications that we can think of.
The extreme scaling computing pattern. This is the alternating version. In the extreme scaling computing pattern we have a primary model, which is represented by the big dot. The primary model runs, and at some point it requires the inputs from auxiliary models. These are started. The primary model then communicates information to the auxiliary models run, and upon their completion they pass information back to the primary model. The concurrent version is slightly different. Here the primary model also runs, but the auxiliary models run at the same time, and both models exchange information between each other. Again, the primary model has a higher computational cost than the auxiliary models. the heterogeneous multiscale computing pattern. In this pattern we have a macroscale model, which is represented by the dot at the top, the grey dot. In addition, we have a HMC manager, which manages microscale information and passes that back to the macroscale model. In some cases, this microscale information is readily available in the database of the manager and it passes it back. However, in other cases, the data is not readily available or not sufficiently accurate, and the HMC manager will then trigger the execution of a microscale model, which is represented by the small dot. Over the course of a simulation, the HMC manager will receive many requests from the microscale model, and as a result, it may return many values and also, for a subset of those requests, perform microscale simulations. The replica computing pattern. In this pattern, we start an ensemble of submodels, which are represented here by the small green dots at the bottom. In this ensemble, there are multiple instances of the same submodel that are being run either concurrently or one after another, but as a set. After these models have completed, they pass information to the other submodels within the multiscale application. This second set of submodels is also run as an ensemble with multiple instances. After this second set is finished, the information is then collected and to be used for further analysis.
Hello, I'm Oliver Perks from ARM. In this section of the webinar, I will be discussing the challenges in utilizing HPC systems for multiscale modeling and how the ComPat project tries to address these challenges. The power of multiscale modeling lies in its ability to leverage vast quantities of computational power. However, these HPC systems are very complicated and highly specialized. This means that learning to use one can be a lengthy process, and transitioning between systems is non-trivial. Application development is an evolutionary process, so considerations of scalability may not have been made in the early stages of model development. The move to HPC systems is driven by scientific delivery, but application performance is key. The goal of the ComPat project is to minimize the time and effort required to transition multiscale models from desktop computing to HPC systems. The formation of multiscale models is done by composing a number of single-scale models together through a coupling framework. The goal of the ComPat project is to assist with the development of the single-scale models and the coupling frameworks required to turn them into multiscale models. When developing and executing these multiscale models, there are a number of considerations to be made. When accessing a new system, you must first build all of the software for the single-scale models. This includes any software dependencies that the models may have. You must then consider which resources are available and any project budget constraints which may exist. Lastly, you will have to consider the performance of these models, both in terms of the single-scale models and the coupling framework. The ComPat project is designed to assist scientists making this process as easy as possible, allowing them to focus on the science. A key component of the ComPat project is the development of a set of tools referred to as the ComPat software stack. These tools are designed to help in the three different phases of multiscale model development. Firstly, to define and compose the model. This phase applies the computational patterns to a selection of single-scale models to define a multiscale model for execution. Secondly, to execute. This is to help run the simulations across different HPC resources. This is done in a simplified and standardized way. Lastly, to optimize. This is to improve resource utilization and also to improve application performance. During the course of this webinar, we will cover these topics and detail some of the tools within the ComPat software stack. This diagram shows how all of the different components fit together as part of the ComPat software stack. It describes the flow of information through the system. We start with the description part, where the multiscale model is composed using the single-scale model definitions. We highlight the use of the middleware and coupling frameworks to enable this composition. The translation service then takes all of this information and produces a set of model configuration definitions. These are then passed to the optimization part, which uses this information about the available systems to form execution plans. These are informed by a performance estimator, based upon historical data analysis and any available performance models. This set of plans is then passed to the execution part to actually schedule the jobs for execution. This resource brokering is performed by the QCG middleware layer. Profiling data from these runs is collected by the ARM map tool and is fed back into the performance database to close the loop. Most research facilities will have their own computational resources. This means that most collaborative researchers will have access to multiple different HPC systems at either an institutional, a regional, or a national level. However, these systems may differ widely. The differences may be in terms of hardware, such as processor architecture, memory capacity, or network fabric. However, the major differences will be felt within the software environment. This may be from the job scheduler which is used on the system, to the file system and location of files. Also, the availability of pre-installed software may differ between systems. These differences can make transitioning simulations between HPC systems very challenging and concurrent usage very frustrating. To make HPC systems more accessible for multiscale computing, we need to make them easier to use by transcending these differences. ComPat provides a unified interface for accessing multiple HPC systems and making the process much easier. The goal of the ComPat software stack is to provide an integrated HPC solution to end users for multiscale computing. At its heart, the ComPat stack uses a customized version of the QCG middleware. This has knowledge of all of the available HPC systems and provides an abstraction layer for job submission. QCG uses an XML job submission script to submit to any HPC queuing system, such as PBS, Slurm, or Load Leveler. Files are moved to the destination HPC system using the Globus Toolkit connector, which QCG then uses to return the results files to the users. On each system, module files are used to manage multiscale model installations and any software dependencies. This enables us to create the correct software environment for the job's execution. In the next part of this webinar, we will expand upon the hardware resources currently available and the job submission and optimization of simulations.
Hello everyone, my name is Vytautas Jančauskas and I work for the Leibniz Supercomputing Center of the Bavarian Academy of Sciences. I am the work package leader of the work package 5 of the ComPat project, which is the experimental execution environment. And I will tell you now what that means exactly. Let's start with the hardware infrastructure of the project. The project has access to 3 different supercomputing sites across Europe. The first one is the SDFC near Manchester. Second one is the Poznan Supercomputing and Networking Center in Poland. And the third one is the Leibniz Supercomputing Center in Garching, Germany. Leibniz Supercomputing Center provides access to the SuperMOOC supercomputer. It is a praise tier 0 machine. It consists of two phases, phase 1 and phase 2, and each provide roughly the same amount of computing power. When it started operation in 2012, SuperMOOC was the fastest supercomputer in Europe. The MOOC in SuperMOOC is in reference to the Munich airport, which has the airport code MOOC. Each phase provides around 3 petaflops of computing power. There are 3 types of nodes that are distinguished primarily by different amounts of memory, which are 32, 64, and 256 gigabytes. There are 12,525 nodes in total. All nodes are various Intel Xeon iterations. Overall storage capacity is 15 petabytes. Poznan Supercomputing and Networking Center provides access to their Eagle machine, which is a praise tier 1 computer. It has a peak performance of 1.4 petaflops. The machine consists of 1,233 nodes. The nodes are all Intel Xeon. Now, Science and Technology Facilities Council, or STFC, Hartree Center provides their NEAL machine. NEAL is an immersion cooling machine, therefore it has a greatly reduced power consumption. It consists of 120 Intel Ivy bridge nodes. In a multi-scale scenario, we will want to make use of all 3 sites to execute different parts of the simulation. Therefore, parts of the simulation may execute on SuperMOOC, other parts may execute on Eagle, and so on. To this end, we need to ensure some kind of uniformity across sites. There are several aspects to this. First of all, we need the users to be able to authenticate on all 3 sites. To this end, each site agreed to accept the same grid certificates. Therefore, a user can use the same certificate to log into each machine in the project. Second of all, we need the same software packages to be available on all machines. We use environment modules with a standardized name structure to make sure that there is a way to load the same software in the same way everywhere. Thirdly, we have a uniform job submission system. The QCG, fully developed by Poznan Supercomputing and Networking Center, is a middleware that can virtually weld computing resources from different administrative domains into a single powerful supercomputing resource. This capability is essential for the ComPat applications to scale up towards exascale performance, while there are only petascale individual systems available. The middleware has been developed in the EU project Grid and later adapted and extended to support requirements of multiscale codes in the Mapper project. Presently, QCG delivers a ready-to-use stack of validated, efficient middleware software components that can manage extremely parallel as well as multiscale simulations. QCG is a mature middleware system which has been deployed in many HPC centers across Europe. The QCG stack consists of a set of components playing different roles in grid and cloud computing scenarios. In a nutshell, the Grid middleware consists of 2 logical levels, grid domain and an administrative domain. Grid level services control, schedule, and generally supervise the execution of end-user applications, which are spread between independent administrative domains. The administrative domain represents a single resource provider participating in a certain grid or cloud environment by sharing its computational resources with both local and external end users. The logical separation of administrative domains corresponds to the fact that they are possessed by different institutions or resource owners. Each institution contributes its resources for the benefit of the entire grid or cloud, while controlling its own administrative domain and own resource allocation and sharing policies. The key component of every administrative domain in QCG is the QCG computing service that provides remote access to queuing system resources. QCG computing supports advanced reservations, parallel execution environments, such as OpenMPI, Proactive, and Muscle. Another relevant service at the administrative domain is in charge of the notification mechanism, and it is called QCG notification. These services are tightly integrated and connected to the grid level services. The critical service on that level is QCG Broker, which is a meta scheduling framework controlling executions of applications on the top of queuing systems via QCG computing services. As part of the ComPat project, a multi-criteria approach for assigning in an optimal way of an entire multi-scale application or its components to the heterogeneous resources offered by the project's test and production infrastructure has been designed and developed as a new module to the QCG Broker service. Different performance and energy consumption characteristics collected from resources allow savings to be made while maintaining the quality of the service required by the user. The system performs multi-criteria optimization with regards to limits on 3 criteria. Electricity needed to carry out calculations. This criterion currently does not take into account other infrastructure-related costs such as cooling, for example. Time to completion, which is defined as the sum of the time of waiting for the resources and the time of calculation, and use of infrastructure time, which is defined as the product of the number of cores and the hours of their use. This criterion has been added to support the most popular method of accounting for used core hours. In further slides, we will discuss energy performance predictions and queue wait time predictions in more detail. The goal of the queue wait time prediction service is to predict the amount of time that a job will stay in the batch system queue. This is needed by the multi-criteria brokering service, which is part of QCG. To this end, we have extended the EEE with capabilities that allow us to store information about each job submitted to each of the computing sites. From this information, we have used machine learning and statistical techniques to estimate the probabilities that a job will stay in a queue for a given amount of time. These probabilities are dependent on the resources requested by the job submitted and the state of the system at the given moment. This information is taken into account when predicting queue wait time probabilities. So for each site participating in the project, we collect information about the scheduler state. Thus, we collect data from all the sites participating in the project. Data collection is done by parsing the output of various scheduler tools. The tools and their output will depend on the resource manager, for example, Slurm, Load Leveler, or PBS that is used on that system. Therefore, for each scheduler, we have to implement a separate data gathering script. All of them work in the following way. The system is monitored until a new job is found in the list of jobs in the system. The jobs are identified by their IDs. The moment a job with an unknown ID appears, it is added to the in-memory list of jobs and its status is tracked. Now, once the job starts running, the amount of time it has spent in the queue is recorded. And once a job is finished, information about that job is added to a database. So this service polls the schedulers every minute. From the technical point of view, this is done by logging into each system using the grid certificate, executing the command that displays the scheduler state, and parsing the results. For each job that's submitted to the EEE, we record 47 attributes that describe that job. For example, the amount of resources that the user requested, how many jobs the user already has running, and how many jobs the user has queued, how many jobs are currently queued in that system, and how many are currently running, what percentage of system resources are currently used, and so on. Based on this data, we predict queue wait times of newly submitted jobs. So we use Bayesian inference to decide what is the probability that a job will stay queued for a given amount of time. This is implemented in a form of a web service that QCG queries. Since the system has real-time access to the machines we are interested in, you only need to specify the amount of resources needed by the job. All the other attributes are taken from the machines themselves. The task of predicting application performance can also be broken down into 2 subtasks. First, we need to collect information about performance of jobs submitted to the EEE. We store parameters that were used when running those simulations and the amount of energy consumed by those simulations. Then we can interpolate and extrapolate from the data when similar jobs are submitted. The performance prediction service is used to model application runtime and thus energy consumption. It does this by fitting mathematical models of expected application performance to historical data that we collect when applications are submitted to the EEE. This service is used to evaluate multiscale simulation execution plans in order to minimize energy consumption. So let us first discuss the database. The primary record in the database is a run. This represents a conceptual simulation. Each run may contain multiple kernel executions, but is contained within a single QCG job. The job ID field is unique and taken from the QCG job ID environment variable during the run. A number of the fields in the run table are aggregated from the associated kernel runs. For example, the energy field represents the total energy consumption of the QCG job. However, depending on the execution pattern of the kernels, this is not just a linear summation. Therefore, we must build logic into aggregation depending on the application and how it was executed. The node type table contains the types of nodes that are available. They are linked to the kernel perf table in order to track per node energy consumption. In the kernel table, we store information about single scale components of the multiscale simulation, or as we call it, kernels. We store problem-specific parameters for each such simulation. We do this in two ways. Firstly, we construct a hash of the problem using an MD5 hash algorithm on the configuration files to the kernel. This hash allows us to perform a uniqueness test when rerunning problems. So we check if we have seen this exact problem configuration before, but perhaps on a different system or on a different core count. Further, we try to extract key performance parameters from these configurations files, such as iteration count, mesh size, spatial information, all of which may impact performance. This information can then be used in the performance prediction phase. We note that this parameters field is stored as a blob type, as we populate it with the JSON object representing the key value pairs of the parameters. The motivation for this is that the available parameters are specific to the individual kernel being profiled and are unlikely to be common between them. This data format makes it easy to interpret these values during the analysis stage for the performance prediction. Finally, the kernel perf table contains the performance information from a specific application run. It is reduced to the key performance metrics of relevance, including ComPat specific metrics such as muscle 2 time. Once we have normalized the performance data to be used in the prediction of the runtime or energy consumption, we extract the performance data grouped by node type. The more historical data is available, the larger this data set is likely to be, and in turn, the more accurate the prediction based upon it. We break up the data into two fundamental components which will exhibit different scaling characteristics, namely CPU time and MPI time. We treat energy consumption at a proportional value to time, first normalizing to a per core power consumption, then extrapolating from there based on the new estimated runtime and core count. For each characteristic, we form a table of core count and value and pass it to the curve fitting routine with the corresponding fitting function for each node type in turn. So we use Python's SciPy curve fit routine to fit each characteristic to an expected scaling curve, and use known properties of the scaling to bound estimations. Such a curve you can see in the slide. The CPU time follows a strict reciprocal relationship as parallel performance is bounded by Amdahl's law. MPI time is more complicated to model, and for this we use a second-order polynomial with an additional base 2 logarithmic term. In the slide you can see an illustration of our estimation for the MPI time. This is for the gem kernel on the PSNC's Eagle machine. Based on our problem size normalization and using our derived fitting function, shown in orange. We also compare this to a standard second-order polynomial, blue dash, fitted to the existing database values, or blue dots. We see how whilst the polynomial is accurate within known data, it trends poorly for unknown data. Obviously, when there is insufficient input data, we run the risk of overfitting. In such a case, we operate on a simplified version of the curve equation. Now, the models themselves you can also see shown in the slide.
In this section, we will provide a summary of the job execution process. Once we have composed our multiscale model, we must turn our attention towards executing it. We have already outlined the current hardware resources of the experimental execution environment. Now we must select the best resources to run our simulation on. This involves selecting the most appropriate node types and core counts for the single-scale models of our multiscale simulation. From this, we can obtain a prediction of the runtime of our simulation. The optimization service uses historical performance data from the performance database to make predictions for new runs. These predictions are for both runtime and energy. The ComPat software stack is designed to help optimize job execution. The optimization service does this by first generating a set of valid plans, which describe the resources for a simulation. Each plan has an associated cost prediction based upon the selected resources. The QCG middleware then selects the best plan for execution based upon the user criteria. These criteria may be to target specific hardware resources or to optimize for parallel efficiency. We can also optimize for time to solution for fastest results, taking into account both runtime and queue time predictions. For green computing, we also support optimizing for minimal energy to solution. To aid with the data collection needed to make such predictions, the ComPat software stack also provides a mechanism to automate benchmarking, making it easy to perform scaling studies.
Hello, I'm Ani Luke from the Max Planck Institute for Plasma Physics. I will show you a short demonstration on how we apply the ComPat software stack to science research such as fusion. Before I go ahead with the demonstration, let's begin with an introduction to the physics. First of all, what is fusion? Well, fusion is a thermonuclear process in which lighter, positively charged particles fuse together under extreme temperature to produce heavier particles, and we're talking about several million degrees. In addition to the production of heavier particles, energy is released as a result of such process. This is the way our sun and other stars power themselves. We want to bring this power source to Earth as it has many advantages compared to other power generation methods. Two of the major advantages are fuel availability and no greenhouse gas contribution. Currently, an international collaboration called the ITER project is constructing a tokamak device to confine the hot plasma using magnetic field. The goal of the project is to demonstrate the feasibility of fusion energy. The picture on the right is the ITER tokamak once construction is complete. To give you a sense of its size, there is an adult human in orange standing in front of the machine. However, this is not as easy as it seems in both experimental and numerical modeling perspectives. Here's why. There are many instabilities generated when a turbulent plasma is hot enough to achieve fusion, and these instabilities can destroy confinement. To predict the performance of fusion device like ITER would require an understanding on how instabilities affect the overall plasma transport. As a simple example, let's take a look at the continuity equation. The particle density in blue relates to the plasma transport. The particle flux in red relates to the plasma turbulence. The particle source in teal is the initial condition, and all terms in the equation rely on the current equilibrium condition. Turbulence, which ties to instabilities, is in the scale of micro to millimeters in space and microseconds in time. On the other hand, the overall transport, which determines plasma confinement, is in the scale of the size of the machine, which is meters in space and seconds in time. As you can see, the scales of the two phenomena are highly disparate. Simulating with only a turbulence code is projected to exceed even the next generation of exascale computers. Therefore, we need to construct a multiscale model that can simulate a wide range of scales. There are many well-tested single-scale models exist within the fusion community, so we decide to take the component-based multiscale modeling approach. We couple 3 single-scale submodels together with initial conditions included. These models are the transport model TRA, the equilibrium model EQU, the turbulence model TUR. We also include a module FDV to convert fluxes from the turbulence model into coefficients required by the transport model. Together, they cover all the terms in the continuity equation. Figure on the left is the topology of our multiscale simulation workflow. Each box represents one submodel, and the arrows represent the data flow. Muscle 2 is the coupling framework we use, which requires a configuration file containing descriptions and parameters to the coupled application. Of all the submodels, turbulence is the most calculation intensive. It is a parallelized code that requires many cores. As for the other models, they require only one core each. Therefore, our multiscale workflow fits into the extreme scaling computing pattern, with turbulence as the primary model and the others as the auxiliaries. Now that we have the design of the application topology, let's take another look at the software stack. With the help of the translation service, we get 2 XML files that provide details in the submodel and multiscale model levels. I'll demonstrate how we apply the software stack to the Fusion application under the extreme scaling pattern, starting from the optimization part. This includes the use of pattern-driven planner to run benchmarks to populate the measurement database and multi-criteria brokering to generate optimal execution plans. Then I'll go over the execution part of the software, which includes the use of QCG pattern-aware scheduler to select the best plan and QCG job controller to dispatch the job. As mentioned earlier, the translation software produces 2 XML scripts. Matrix.xml contains details for each submodel. For example, the snapshot on the left shows the description for turbulence model. It contains the restrictions to the number of CPUs. In this case, it is 2 to the x power, with x ranging from 7 to 11. All the available resources for the model are also listed here. On the other hand, multiscale.xml contains details to the multiscale workflow. As you can see on the right, that includes descriptions to the submodel coupling topology, along with specifications such as middleware, QCG, coupling framework, Muscle 2, and the configuration file, unify.cxa. Once we have the matrix and multiscale XMLs, we can easily run benchmarks on every available resources with various numbers of CPUs. All we have to do is to send these 2 XMLs to the pattern-driven planner. The -B option is for benchmark. And immediately the pattern-driven planner studies the XMLs and figures out that there are 5 variations to the number of CPUs based on minimum and maximum number of CPUs, specified in the matrix XML. And there are 5 available node types, therefore we have a total of 25 benchmarks. Here are the individual execution plans for the benchmark. Let's submit all of them to the QCG. Once the benchmarks start running, the map tool integrates into Muscle 2. Map then measures every submodel's performances and populate the measurement database. This will help the pattern-driven planner when it comes to designing optimal execution plans, as you will see in the next video. You can check the status of all the jobs and which machine the job is sent to, as you can see here. The pattern-driven planner allows the end user to define desired performance metric. whether it's runtime, which is the metric of choice when you want your results as soon as possible, efficient use of resources, which is the metric of choice when you want to spend the least amount of CPU hours, or energy, which is the metric of choice when you want your job to consume the least amount of energy possible. So let's use the default setting. The -O option is to name the output. The -MC option is to access multi-criteria brokering, and the -M10 is to look at the 10 most optimal plans. The pattern-driven planner then studies the previous profile measurements accumulated in the database and generates optimal plans based on the metric we specified. Since we didn't specify a performance metric, multi-criteria brokering takes the default, which is the runtime. Here we see the plan ID arranged from the lowest to the highest runtime. Each plan also contains the number of cores per submodel, energy consumption in joules, time spent in auxiliaries and primary model, node types, and resource usage in CPU hours. Let's submit the plan to the QCG pattern-aware scheduler. We can also check the status of the job. So here we type QCG-info. So while the current status is in queued, let's take a quick look at the runtime.xml. So the pattern-driven planner produced an XML that contains the most optimal execution plans with details including the time, energy, the node type, and the number of cores for the auxiliaries and the primary model. So it also has a decision section for the QCG scheduler. It has 3 possible performance metrics listed with the limits and a weights assigned to each metric. Since we chose runtime as our metric, a weights factor of 1 is assigned to the time limits. As for the weights factors for others, it's 0. So let's check the status again. It is now pending. So basically, QCG Scheduler evaluates the node status of every execution plan given by pattern-driven planner and then eliminates any plans that require nodes that are not currently available. Then for the rest of the plans, it takes the estimated queue time of the node type into consideration. This queue time, which is provided by the queue time prediction service, is combined with the runtime given by the pattern-driven planner to do its own take on the cost. It then chooses the plan with the lowest cost value. Here it chose plan 3. QCG follows through with plan 3 and sends the job to the Eagle Haswell 64 node types with 2052 cores. So while we wait for the job to run, we can see what kind of execution plans pattern-driven planner it generates when other performance metrics are defined. So let's look at the resource setting. So here we can see that there are also 10 plans listed that are sorted by from the least resource usage to the highest resource usage in CPU hours. And now let's play with the different option. Let's take a look at if we were to choose the energy metric, the pattern-driven planner would generate different sets of plans. And here, as you can see, the plans are listed from the least energy consumption to the highest energy consumption. And of course, you can see the node types are different for each of these plans, or not necessarily the same. Now, once the job completes, all the outputs get staged out, and these are the output files. These runs are rather short, with only a total of 4 iterations. We use the same multiscale topology and run a tokamak scenario for several thousand iterations. Through these types of production runs, we were able to study the time evolution of electron heat flux and temperature. An example is shown on the figure on the left. We also studied the plasma when it reaches quasi-steady state. The spatial profile of the temperature at quasi-steady states is displayed in the figure on the right. For more details into these results, please refer to our work that will be published in the near future.
Hi, I'm Maxime Vassot from UCL. So we've just finished the first demo on the extreme scaling computing pattern, and we are now moving to the second demo of this webinar, which is going to deal with the heterogeneous multiscale computing pattern. So we've chosen to illustrate the heterogeneous multiscale computing pattern, or HMC in short, with our materials application. In that application, what we do is we try to model the behavior of materials depending on their chemical specificity. That means we are going to simulate simultaneously the behavior of their chemical structure and the behavior of the macroscopic structure that's going to be made with that material. At the continuum scale or macroscopic scale, the one where we're going to have the real design of the structure, we're going to use finite element modeling to predict the mechanical response of the material. Such methods usually use constitutive equations to relate stress and strains, but instead of using the classical way, which depends on constitutive modeling and therefore equations that are phenomenological or based on human assumptions, we're going to use molecular dynamics modeling at the nanoscale or as a micro model to replace those equations. Basically, what's going to happen, as you can see on the right in the picture, in each cell of the finite element model, we're going to run a molecular dynamics simulation that's going to predict the stresses in the system depending on the strain that are applied on it. These strains are going to be derived directly or obtained directly from the finite element simulation at the macro scale. So in the end, what you get is a computational workflow that basically synchronizes the evolution of many molecular dynamic simulation using a finite element model. So more specifically, that means that you have a workflow that's an alternance of two phases. The first phase is the simulation of the finite element model, which is really quite small. You run it on one or few nodes. And on the other side, you have a second phase that's way more computationally intensive, which consists of the simulation of all the molecular dynamic system that needs an update. That means that you can run up to as many molecular dynamics simulation in an iteration as you have cells in your finite element system. Each of these molecular dynamics simulation is already quite more computationally intensive than the computation of the finite element model. But the good thing about that workflow is that each of these molecular dynamic simulations are totally independent. That means you can run them in parallel without absolutely no communication, which makes the computational efficiency of the HMC pattern. As you have all these molecular dynamic simulations to run in parallel, and that the execution time is highly variable, the key point to have a computationally efficient HMC pattern is going to be the execution and actually the scheduling of all these molecular dynamics simulation. The naive way to schedule and execute all your molecular dynamic simulation when you don't have any of the ComPat tools available, and therefore you don't have any knowledge a priori about the execution time of your microjob, is to take your total allocation and split it in a number of small batches which have an equal amount of cores themselves, and to queue your microjob simulation in these different queues. The problem that can arise with such naive way of queuing your microjobs is that if you put all your microjobs that have the longest execution time in the same queue, this queue is going to terminate a lot later than the others. The first reason for the inefficiency of that naive way of queuing your micro jobs is that if the blue job actually finishes before the red job, you would like to be able to execute the job that's coming after the red job in the queue of the blue job. So to summarize this first problem that we'll try to deal with later is that the naive way of queuing your jobs lacks of flexibility. The second reason for which this naive way of scheduling your molecular dynamics job is quite inefficient is because in the heterogeneous multiscale method, all the MD simulation of molecular systems have a constant strain rate. And since the strain applied to each of these systems is different, they all gonna end up having a time to completion different. So if you give each of these molecular dynamic systems the same number of cores, which is what we assume in this naive way of scheduling, they're all gonna end up at different times. So even if you don't have any queuing going on and you just execute all your molecular dynamics jobs in parallel, you're going to have an important amount of idle time on each of your processes. You can see that in the picture in the middle of that slide. Basically, the white part of this diagram is when the cores are being used, and the dark part is the time where they are not being used. And so we can recap the second issue of that naive way of scheduling by saying that due to the fixed allocation of resources to each of the molecular dynamics job, you end up having significant load balancing issues. Now, if we want to move away from the issues raised by the naive way of queuing jobs, what we can do is start using services provided by ComPat project. The first tool we're going to use is the QCG Pilot Job Manager. The Pilot Job Manager helps us by centralizing all the micro jobs that have to be run in a single queue. Basically what happens is that anytime an execution slot is becoming free because the job it was running has finished, a new job is taken from the queue and executed into that slot. The Pilot Job Manager basically executes the micro job in the first in, first out order. That means that as soon as one of the execution slot becomes open, because one of the molecular dynamics jobs just finished, the Pilot Job Manager is going to check into the queue and find the first job that can fit into that slot in terms of resources. Using the Pilot Job Manager basically removes the issue number one that we mentioned earlier, which was lack of queuing flexibility. A second benefit of the Pilot Job Manager is that it forces the user to separate the allocation from the micro jobs from the macro jobs. Namely, each molecular dynamics simulation is going to be run on its own allocation. The benefit from that is that if one of the MPI communicator from any of the molecular dynamics job fails, the rest of the simulation can continue. The use of the Pilot Job Manager is relatively straightforward. It can be done in two ways. The first one is a static version that relies on JSON file. The other one is a dynamic version that is based on a Python interface. The difference between the two is that in the first one, the static version, before executing the Pilot Job Manager, you have to provide it with a JSON file containing the list of all the jobs in the order that it will be executed by the Pilot Job Manager. In the second one, the queue of the Pilot Job Manager is running throughout the whole simulation, and you can add to it using the Python interface a new molecular dynamics simulation that will be run concurrently. So we've introduced the Pilot Job Manager, which helps solving the issue number one, namely the lack of flexibility of the queuing system. Now we're going to try to tackle the issue number two, which is going to be done by actually optimizing the way we built the JSON file submitted to the Pilot Job Manager. The issue number two, namely the load balancing issue faced using the naive way of queuing the molecular dynamics job, was mainly due to the fact that each of the molecular dynamics job has a different execution time. So in order to improve the way we queue the jobs and actually allocate them resources, what we need to know is actually how long they're gonna run for. To do that, we are built a performance database of the molecular dynamics simulation. In this database, you can find the execution time for a large amount of these molecular dynamics simulation with various input parameters. The input parameters being the number of processes given to one of these jobs and the strain tensor applied to it, which in the case of the material application are the only two parameters that the micro job can have. So as you can see on the left part of the screen, given a certain number of cores, the molecular dynamics simulation scale pretty linearly with the norm of the strain tensor. Now that we've fully established how we can run a multiscale simulation using the ComPat software stack, we're going to make a demonstration of the HMC application. For that purpose, we're going to simulate the behavior of the shell that you can see on the screen. This shell is made of a nanocomposite of graphene and epoxy resin. The shell will be facing a high velocity impact in its center. The animation you see on your screen right now shows basically the behavior of the macroscopic model, finite element based model of that shell. That shell contains 700 filament cells and is going to be run for 5 iterations. And this is going to be run over 100 nodes, total allocation. So let's see how it goes. So first thing you have to do is to log in on the QCG client. Once you're there, you have to load the QCG ComPat module, which I have done now. So to execute the simulation, you need to provide the XML file with the details of the simulation. So I'm going to show you the script that's been produced by the translation services of the ComPat stack, especially for the HMC application. So here it is. So at the beginning you have the plans, the execution plans with the detail, the number of cores allocated for a certain amount of time to the main application, and then you provide details here about the application itself, and then where to get the input files in those 3 lines, and where to stage out the output files. So now I'm actually gonna execute the command. So it is relatively simple. It is done like this. So now the simulation is gone. Let's see the details about it. So as you can see on the screen, the simulation has been sent on Eagle and is actually pending at the moment. And the file for that simulation have been sent locally to Eagle at this address, which we're gonna check right now. Now let's have a look at what's happening on Eagle directly. So I'm gonna log to Eagle directly, and I am going to go to the repository of the simulation. So if we look what's inside, you can actually see what's happening. So the simulation started, as you can see, some parameters have been initiated, and then the first iteration has started. So in the first iteration, no MD simulation has been run, but in the second one, you can see here the list of the cells that requires an MD update. So all of these files have been sent to the optimization service, which produces in turn the JSON file with the list of the jobs. And you can see at the bottom that the job has been submitted using the pilot job manager. So if we have a look at what's happening on Eagle, excuse me. So you can see that the main simulation is running and the pilot job manager associated allocation is still pending and is going to run on 95 nodes, which is the optimal found by the optimization service, while we requested 100 nodes. And if we have a look at the JSON file with the job list that has been produced, you can find it in the following repository. It is a bit rough if we look at them, but so here is the complete list of the molecular dynamics job in a JSON format. But if we actually look at it with the text editor, it becomes a lot more clearer. So here you have the list of the molecular dynamics simulation that have been run. They are ranked in order of decreasing core count. So as you can see, it ranges from 14 nodes, to the minimum value, which is 1. And we can find all the simulation we've been asking for. The simulation of the shell on which the demo has been conducted has been used to compare all the tools that we've been presenting before. So in that situation, we have been testing 3 different configurations. The first one without the pilot job manager, a second one with the pilot job manager but no optimization, and a third one with the pilot job manager and an efficiency optimization method. You can see on this slide the comparison of the total execution time of these 3 configurations on 2 types of allocation, one on a small one, 20 nodes, and on a bigger one, 100 nodes. Independently on the size of the allocation, using a pilot job manager makes always sense. If you compare the green and the blue curve, you can see up to a reduction of runtime up to 70% in the case of 20 node allocation, or at least 40% in the 100 node allocation. Using the optimization method, however, decreases the runtime only in the case of a small allocation. We can see that on a 100 node allocation, there is a slight increase of runtime using the optimization method. Let's now have a look at a more detailed benchmarking result of the 2 configurations, including the pilot job manager. This comparison is done on the case of 100 nodes allocation. So these results show at the top the utilization percentage, which goes from 0 to 1 in the case of where all the processors are being used. In the second line, the number of microscale jobs, and in the third line, the number of processors used in average per job. Looking at the utilization percentage, we see that in these both cases where we use the pilot job manager, we make use of 100% of the cores throughout most of the simulation. The only time where the number of cores being used decreases is when we don't have any more jobs left in the queue to be executed. These more detailed benchmarking results also show why we didn't see any improvement using the efficiency optimization method. In the first iteration of that configuration, we can see that only 60% of the core are being used. It's because all the molecular dynamics jobs are run simultaneously, and the allocation actually given is too large, so 40% of it is not actually even used. But if we compare the last 3 iterations, you can see that the efficiency optimization method is actually faster than without the optimization.
Now that you have seen a demonstration of the ComPat software stack in action, we will take the opportunity to conclude this webinar and reiterate some of the points that we have covered during it. During this webinar, we have shown the value that multiscale modelling has in addressing some of today's biggest scientific challenges. We have shown how computational patterns can help improve the modularity of scientific applications and ease their development. And we have shown how these techniques are helping to scale these algorithms to the next generation of large-scale HPC systems. However powerful these HPC systems are, they still present ease-of-use challenges to application developers. During this webinar, we have presented the ComPat project and illustrated how it can make developing and executing multiscale simulations easier and faster for modern HPC systems. One of the core principles of the ComPat project has been the development of the concept of computational patterns for multiscale modelling. These patterns help to define the flow of information within a multiscale model. As such, they can act as templates to help speed up the development of a multiscale model, and act as a guide on how to compose the single-scale models and which software tools to use. The nature of computational patterns has also been used for automation within the project, helping to generalize behavior based on pattern rather than relying on application-specific coding. We have also shown how ComPat provides flexible access to multiple HPC systems through the experimental execution environment. By providing a consistent interface, we have hidden away machine-specific complexities behind an abstraction layer. This provides a unified job submission format with file movement and even support for application profiling. Further, our approach provides a consistent software ecosystem for running the jobs. All of this means that by using the ComPat software stack, users can develop their application once, but deploy simulations across multiple HPC systems with minimum modification, again allowing the scientists to focus on their applications rather than the nature of the HPC systems. The ComPat software stack provides multiple opportunities for runtime optimization of multiscale simulations. By taking a holistic approach to resource management, the system has oversight of the available resources, allowing for resource brokering through QCG and application tracking with profiling of runtime and energy metrics. Combined, this information can be used for historical performance analysis, allowing it to generate runtime plans with corresponding performance predictions. The system can then optimize the execution through the selection of plans based on user optimization criteria. In conclusion, the ComPat project makes HPC resources easier to utilize for multiscale simulations. Through the patterns, we help build scalable models for next-generation science. And through the tools, we then provide their means to speed up the development and deployment of these simulations. Our solution hides the complexity of HPC systems behind abstraction layers, preventing the user from having to worry about the underlying systems and letting them focus on the science.
This is Hugh Martin. I work for CBK Scicon, an e-science consultancy in the UK. I just wanted to mention a few resources for you to take away from this webinar. Firstly, Muscle 2, which stands for Multiscale Coupling Library and Environment. This is a toolkit which implements a number of concepts of the multiscale modelling and simulation framework, and which enables the coupling of single-scale models to create, deploy, and execute multiscale applications. Muscle 2 has been adopted by multiscale applications across numerous scientific domains and supports the execution of applications with cyclic dependencies, as well as those which require execution using heterogeneous or even distributed infrastructures. Muscle 2 supports Java, C, C++, Fortran, and Python code with MPI, OpenMP, and threads. For more information, please see the publications shown on this slide. You can also download Muscle 2 from the Software Resources page on the ComPat website. FabSim is a toolkit developed to simplify a range of computational tasks for researchers in diverse disciplines. It provides a systematic way to automate the use of resources, including HPC and distributed machines, and to make tasks easier to repeat by recording contextual information. For more information, please see the publications shown on this slide. You can also download FabSim from the Software Resources page on the ComPat website. The Astrophysical Multipurpose Software Environment, also known as a MUSE, is a software framework that provides a homogeneous interface to a wide variety of packages, which enables the research of astrophysical phenomena where complex interactions occur between different physical domains. The framework can be used for astrophysical simulations in which existing codes from different domains such as stellar dynamics, stellar evolution, hydrodynamics, and radiative transfer can be easily coupled. For more information, please see the publications shown on this slide, and you can also download a MUSE from the Software Resources page on the ComPat website. The QCG middleware, previously known as COSCOS Grid, is an integrated system offering advanced job and resource management capabilities to deliver to end users supercomputer-like performance and structure. By connecting many distributed computing resources together, QCG offers highly efficient mapping, execution, and monitoring capabilities for a variety of applications, such as parameter sweep, workflows, MPI, or hybrid MPI OpenMP. Thanks to QCG, large-scale applications, multiscale or complex computing models written in Fortran, C, C++, or Java can be automatically distributed over a network of computing resources with guaranteed quality of service. The middleware provides also a set of unique features, such as advanced reservation and co-allocation of distributed computing resources. For more information, please see the publications shown on this slide, and you can download QCG from the Software Resources page on the ComPat website.
The ComPat project made use of the commercial HPC tools from ARM. ARM Forge is a suite of parallel tools for HPC application developers, containing the DDT debugger and the map performance profiler. Both map and performance reports were used to collect and analyze performance data from multiscale applications through the use of existing and ComPat-specific custom metrics. For more information about these tools and their uses, or to apply for a trial license, please contact ARM via arm.com/HPC or directly at ollie.perks@arm.com.
VECMA, or Verified Exascale Computing for Multiscale Applications, is an EU Horizon 2020 funded project that is something of a spiritual successor to ComPat. VECMA aims to enable a diverse set of multiscale multiphysics applications, from fusion and advanced materials through climate and migration, to drug discovery and the sharp end of clinical decision-making in personalized medicine. VECMA will enable these to run on current multi-petascale computers and emerging exascale environments with high fidelity, such that their output is actionable. That is, the calculations and simulations are certifiable as validated, verified, and equipped with uncertainty quantification by tight error bars such that they may be relied upon for making important decisions in all the domains of concern. The central deliverable of the project will be an open source toolkit for multiscale VVUQ based on generic multiscale VV and UQ primitives, to be released in stages over the lifetime of the project. Fully tested and evaluated in emerging exascale environments, actively promoted over the lifetime of the project, and made widely available in European HPC centres. You can read more about VECMA on the project website www.vecma.eu. You can also keep up to date with us via our Twitter account @vecma4. Finally, for more on the ComPat project, visit www.compat-project.eu. You can also follow us on Twitter @ComPatProject. You can also see our YouTube channel by searching for ComPat Project. If you have any queries, please send them to me at h.martin@cbkscicon.com. Thank you all for tuning in, and we will now take any questions you have.